This is a week 10 of engineering thermodynamics course online session. So this week we are looking at entropy in extension to the second law. So the second law we saw statements regarding how heat can flow or how energy can be converted, and next with that statements we have Clausius inequality which comes in, which states that for an reversible cycle you have delta Q by T should be always less than or equal to 0, which essentially says can be written in terms of entropy, which says your entropy is always increasing for an isolated system or equal to 0. Either it can increase or it is equal to 0. So that's the total case. So what it says, you have any process occurring, your entropy generated in the system and the surrounding, which in total is an isolated system. The universe is an isolated system. So that entropy, the system plus surrounding, will always be rising. So entropy is always increasing. So that's why ds is greater than or equal to 0. Only in the case of reversible process which you can have is 0. So the reversible adiabatic process, with a reversible cycle, you have entropy to be 0. So the best example is your Carnot cycle, where your entropy generated is 0. So with that idea, we can extend it to any process, just like how we did the energy balances, like first law for a system. You can apply an entropy balance as well for a system or a process, and that's what we will look at for some examples, how to solve this for a process and how to apply an entropy balance to a process and estimate what is the entropy generated. So we'll proceed to see some problems on the same. So the first is we have 5 kg of nitrogen which undergoes a process from pressure of P1 equals 5 bar and T1 of 400 Kelvin to a pressure of 2 bar and a temperature of 500 Kelvin. So this is the process in which the nitrogen is going. So initially it is at 5 bar and 400 Kelvin, and it goes to a second state where the pressure is 2 bar, there is a reduced pressure, and your temperature is increased from 400 Kelvin to 500 Kelvin. So this is the two states through which the process is going. So what has been given is we need to assume this to be an ideal gas behavior. We need to determine the change in entropy in kilojoule per Kelvin when we assume a constant specific heat, which is we assume a constant specific heat. The value, you can use it at a mean average temperature of 450 Kelvin, and then the second case when you have a specific heat which is varying across the temperature. So kind of an ideal real behavior where the fluids or gases specific heat varies. So let's see how to solve this. So for an ideal gas with constant specific heat, we can write delta S as Cp ln T2 by T1 minus R ln P2 by P1. So how do we get this? So it's an ideal gas behavior. So PV equals to RT, P to small v specific volume equals RT. So that is one equation, and you will get dH equal TdS is dH minus VdP. So substituting V in terms of pressure and integrating and dividing throughout by temperature, so you get ds equals dH by T. So dH you can write it as Cp delta T. So you have Cp by T into delta T. So integrating that, you get Cp ln T2 by T1 minus you will have R by P, because V is RT by P and you are dividing by P. So you will be left out with minus R by P dP. So integrating, you get minus R ln P2 by P1 for two end states. So the change in entropy can be given for a ideal gas behavior and a constant Cp. That reduces to this equation here, delta S equals Cp ln T2 by T1 minus R ln P2 by P1. So it's a simple equation which we got from one TDS relation. So TDS dH minus VdP, and then assuming PV equals RT, it's an ideal gas behavior. So from the table of nitrogen gas for 450 Kelvin, we can find out the Cp comes out to be 1.049 kilojoule per kg Kelvin. So assume this has to be given. So Cp is 1.049 kilojoule per Kelvin. So that because we are assuming Cp is to be constant, we can straight away plug in the Cp value here, and we know the initial and final pressures as well as initial and final temperature. So we can find out the delta S. So the only remaining unknown is R. So R can also be found out using the universal gas constant and the molar mass of nitrogen. So we know molar mass of nitrogen is 28. So 8.314 divided by 28 gives you R in terms of kilojoule per kg Kelvin. So substituting the values, we get mass given as 5 kg and Cp is 1.049 kilojoule per kg Kelvin from the nitrogen table, property table, and then ln T2 by T1, T2 is 500 Kelvin and T1 is 400 Kelvin. So substituting that and minus R value into ln 2 by 5. End pressure is 5 and the initial pressure was, so end pressure is 2 and final pressure was 2 and initial pressure was 5. So ln 2 by 5. So that gives you 2.53 kilojoule per Kelvin. So this process is possible. If you see, delta S is positive. So this is just the delta S of the process occurring. So if you consider the system containing nitrogen undergoing this process, so this delta S is of the system or of the nitrogen undergoing the process. The next is when you are assuming that your specific heat is not constant. So the first case was when you are assuming specific heat to be a constant value throughout the process, but in an actual case that will not be the case. The Cp value will vary throughout the process. So to find that, what we can do is we can straight away find out M is the change in entropy because of temperature minus the change in entropy because of pressure. You can write it in terms of two parts. So this is for constant pressure. What is your, so the entropy change with respect to temperature, and then we substitute what will be the change with respect to the change in pressure. So if you do that, so mass is here is still what we are assuming is the Cp is not varying with respect to pressure. So because the pressures also are not that far apart, so it's 2 bar and 5 bar. If the pressure differences are very large, like 100 bars and 2 bar, in that case you have variation in Cp value with respect to pressure as well. You will have property variation with respect to pressure. So for in this case we are assuming a simpler case. So we are assuming just the entropy to be a function of temperature. So substituting the values for this, we get entropy value for 500 Kelvin and 400 Kelvin in terms of molar quantities. So we are dividing by molar mass to convert it back to kilojoule per kg Kelvin. So this is what we get, and similarly the pressure part will remain same as minus R ln P2 by P1. So substituting, we still get 2.531 kilojoule per Kelvin. So what this says is assuming it to be an ideal gas holds pretty good because the states are not far apart or are not very different. So the pressures are low and you have high temperatures. These are the cases where the gas is behaves as an ideal gas. So this result could be significantly different when the temperature ranges were greater, or you have a very large difference in pressure. So you, in that case, the values with this assumption will be too far apart from the assumption with varying specific heat. So moving on to next question, we have ethylene gas C2H4 which enters a compressor operating at steady state at 310 Kelvin and 1 bar and is compressed to 600 Kelvin and 5 bar. Assuming the ideal gas model, determine the change in specific entropy of the gas from inlet to exit in kilojoule per kg Kelvin. So the previous case, if you saw, what happened is your pressure reduced and your temperature increased. So that is some combination of process is happening, but we were concerned only with the end states and we estimated what is the change in entropy. So here there is a compression process which is happening for ethylene. So a similar kind of approach which we will take. So we have initial temperature and pressure known, 310 Kelvin and 1 bar, and this ethylene gas is being compressed to 5 bar and 600 Kelvin. So both pressure and temperatures are known. So and again we are assuming it to be an ideal gas model. So PV equals RT holds true. So finding out delta S is again delta S is Cp ln T2 by T1 minus R ln P2 by P1. So that is true. So this is what we get. So here we are saying that I think question is incomplete. So here we have given that ideal gas follows the ethylene gas follows this ideal gas model of 4 order polynomial for Cp as a function. So it's a function of temperature. So instead of integrating, assuming Cp to be constant, we are assuming Cp is a variable of temperature divided by T. So integral T1 to T2. So substituting that expression, we get the integrating, then we get R is alpha ln T2 by T1 plus beta T2 minus T1 plus gamma T2 square minus T1 square by 2 and delta and epsilon. So we have 4th order polynomial which you are getting, and this when you are substituting the temperatures and the coefficients which are given in the problem. So what we get is 1.3311 kilojoule per kg Kelvin. So that is the entropy change because of the temperature change. And now the total entropy change will be again delta S is the integral T2 by T1 to T to Cp by T dt. So this is we have found out, and this is with respect to temperature change, and with respect to pressure change is minus R ln P2 by P1, which we already know, which is varying from the final pressure is 5 bar and initial is 1. So R ln 5 by 1. So that comes out to be 0.8541 kilojoule per kg Kelvin. So to see if this ideal gas this thing applicable, we can straight away see what is the compressibility factor. So if compressibility factor is 1, close to 1, that says this ideal gas can be applied. So moving on to next question, we have a system consisting of 2 kg of water initially at 160 degrees Celsius and 10 bar, which undergoes an internally reversible isothermal expansion during which there is energy transfer by heat into the system of 2700 kilojoules. So determine the final pressure in bar and the work in kilojoule. So the process says that it's internally reversible, and you have an isothermal expansion. So your temperature is constant, and they say it's an reversible process. And what else is given is the initial condition. We have 2 kg of water, and they say the water is initially at 160 degrees Celsius and 10 bar. And during this process, you have additionally heat which is being added, so which is leaking in. So it is to around 2700 kilojoules. So we need to find out what is the final pressure and the work done. So how do you solve this? So if you see, this is the process. You have expansion process, so you can equate it to a piston cylinder arrangement where you have expansion. So you have initially water which is at 2 kg, and you have heat which is coming in at 2700 kilojoules, and the initial temperature and pressure is known, and this is doing some work. So we need to find out when how the process will look it in a TS diagram. So you have at initial 10 bar, and because you are expanding, your pressures will come down, and so if you go along a TS diagram, if you go horizontally, so you have temperatures being constant. So initially you are at this subcooled condition, so where you have a 10 bar, and you are entering to a pressure where you will you have the saturated condition, and then you will move into two phase. So along till it reaches a saturated state, you will have a reduction in pressure, and then you have your temperature and pressure being constant, but your volume changes. So initially you start here at 1, and then you are somewhere at 2 here. So we need to find out what is the final pressure. So what we know is that the process is internally reversible. So it's a reversible process. You can write the entropy change to be delta Q by T. So that's what you get if in a Clausius inequality, you have for a reversible process a cycle, you have delta Q by T equals 0 for a reversible case. So for that is for a cycle. If you have taking any two state points and you are varying, then it's dq by T is equals to ds. So that's what you write for reversible case. So you can write. So from here you can find out the relation between the entropy and the heat which is coming in. So Q internal reversible is T into S2 minus S1, and if you are writing it through specific quantities, you have mass in times temperature multiplied by S2 minus S1. So what we know initially is initially the water is at 160 degrees Celsius and 10 bar. So that there your from the steam table you can find out what is your entropy. So S1 it comes out to around 1.9427 kilojoule per kg Kelvin, and S2 now we know S2 we know S1, the initial condition S1, we know the mass, we know how much Q has been added, so we can estimate the S2, and since the temperature is constant, we also know the temperature because it's an isothermal expansion, we know the temperature. So S2 is S1 plus Q internal Q divided by mass times the temperature. So substituting the values, we get S2 to be 5.0605 kilojoule per kg Kelvin. So that is your second state point which we have found out. So now we have to just go through the steam table and look at where S2 is corresponding to 160 degrees Celsius, at what pressure we are getting this. So from a saturated 160, that is saturated pressure which you will get. So that is your pressure. So that is 6.178 bar. See, because as explained, you have from 10 bar your pressure will vary, and you will reach a state where at a saturated condition the water will start boiling and you'll convert it to vapor, and your volume is still expanding because whatever liquid is getting expanded to steam, and but your temperature is remaining same, your pressure is remaining same. The whatever energy you're you're losing, that is getting converted into steam. So you are still in the expansion process. But your pressure will remain same. So you are at the final state. We are just concerned about the final state. So there, if your entropy is still lying between your gas entropy and your liquid entropy, you are in two phase. So that pressure will be corresponding to your saturated temperature, which is 160 degrees Celsius. So that is the pressure here, which is 6.178 bar. And at this point too, so we know the saturated vapor and saturated liquid entropies. We can find out the dryness fraction or quality. So that comes out to be 0.649. So work done is Q plus mass into U1 minus U2, which is your first law. So just like entropy, we can find out internal energies, so which comes out to be 674.86 kilojoule per kg, and U2 is again using the quality, we can find out U2, which comes out to be 1903.77 kilojoule per kg. So the total work done we can find out is Q plus M into U1 minus U2. Substituting, we get the work because of the expansion done by the system is 242.2 kilojoules. So next we're moving on to next question. So a gas initially at 2.8 bar and 60 degrees Celsius is compressed to a final pressure of 14 bar in an isothermally internally reversible process. Determine the work and heat transfer each in kilojoule per kg of gas. If the gas is A, refrigerant R134A, and B, air as an ideal gas, sketch the process on a PV and TS coordinate. So what is given is you have a gas, so you are initially at 2.8 bar and 60 degrees Celsius, and it is being compressed to 14 bar in an isothermally internally reversible process. Your temperature remains constant, so initially you are at 2.8 bar and 60 degrees Celsius, and finally you are reaching 14 bar and 60 degrees Celsius, and this is happening at a isothermal internally reversible process. And we need to find out what will be the work and heat transfer for two cases: when it is the gas is a refrigerant R134A, and the second case when you are using air, which is an ideal gas. So the assumption which you are making is the gas is in a closed system. The compression takes place isothermally and has no internal reversibility, which is given, and you are neglecting kinetic and potential energy. So just like in the previous problem, we know the relation between the delta S and the heat transfer for an internal reversible process. So ds is dq by t. So we can write q as integral t delta S, and since the temperature is constant, so we can take it temperature out. So what we get is m t s2 minus s1, or q by m is t s2 minus s1, and the energy balance, what you get is delta U is q minus w, which is your first law. So dividing again this by mass to convert it into specific quantities, we get the work done by m equals q by m plus u1 minus u2. So now for R134A, for 2.8 bar and 160 degrees Celsius, we can find out what is the U1 S1, and similarly for 14 bar and 60 degrees Celsius, we can find out the UNS. So substituting this in the above expressions for Q and the W expression, So first we will find out Q. So Q by M is 60 plus 273 to converting temperature into Kelvin multiplied by the change in delta S. So the initial delta S is 1.1079. So final minus initial. So 0.9297 minus 1.1079 multiplied by 273 plus 60. So that gives you minus 59.34 kilojoule per kg. This is the amount of heat which is rejected, and then the total work done for compressing the gas is Q plus U1 minus U2. So U1 is 277.23 minus 262.17 minus 59.34, which is the Q. So the total work done per kg of refrigerant is minus 44.28 kilojoules. So this is for the refrigerant R134A. But if you assume it for an air which is an ideal gas, so in that case we can straight away assume use the same relation which we used in the previous problem. Delta S is Cp ln T2 by T1 minus R ln P2 by P1. So in this case what happens is, since your temperature is constant, so ln T2 by T1 becomes ln1, which is 0. So we get S2 minus S1 is minus R ln P2 by P1. So your molar mass of air is 28.97. So R is 8.314, which is the universal gas constant, divided by 28.97 multiplied by your ln of 14 bar, which is the final pressure, divided by 2.8 bar. So that gives you delta S to be minus 0.46139. So since now we know delta S, we can find out Q. Q is T delta S. So 333 Kelvin 333 multiplied by your delta S, that gives you Q to be minus 153.81 kilojoule per kg. So this is the amount of heat which has been rejected for air, and since your temperature is constant and we are assuming ideal gas, so Cv is constant, so U1 minus U2 will become 0. So whatever work is generated is equals to the whatever heat is rejected. So W is equals to Q, which is minus 153.81 kilojoule per kg Kelvin. So this is the amount of work which is required to compress air. So moving on, next question. We have nitrogen which undergoes an internally reversible process from 6 bar and 247 degrees Celsius, during which PV raised to power 1.2 equals constant. So that is your process bar. So the initial volume is 0.1 meter cube and the work for the process is 121.14 kilojoules. So assuming ideal gas behavior and neglecting kinetic and potential energy effects, determine heat transfer in kilojoule and the entropy change in kilojoule per Kelvin. Show the process on a TS diagram. So we have nitrogen and the process equation is given, so which is PV raised to power 1.2 equals constant, and also it's been said that it is an internally reversible process and the initial condition is 6 bar and 247 degrees Celsius and the initial volume is 0.1 meter cube. The work done is also given, which is 121.14 kilojoule. So we need to find out what is the heat transfer and what is the entropy change, and also plot it in a TS diagram. So we know it's in polytropic process. The work done can be expressed as, so we know work is integral P delta V. So from V1 to V2. So we know the process equation, so we can write it as C by V raised to power n. So integrating, what we get is P2 V2 minus P1 V1 divided by 1 minus n. So this is the expression for work done for a polytropic process. So P2 V2 can be written in terms of temperatures because we are assuming it by ideal gas. So it becomes Mr T2 minus T1 by 1 minus n. So substituting the values, we get you can find out the final temperature T2, because that is the only unknown. We know the initial temperature, we know the work done, we know mass. So the only unknown is the final temperature, which can be found out. So to find out mass, we know the initial pressure, the volume and temperature, and we know the gas. So if I know R, so substituting M is P1 V1 by R T1. The initial pressure is 6 bar, so the volume is 0.1 meter cube, and R is 8.314 divided by 28 for nitrogen, multiplied by initial temperature is 247 degrees Celsius, 247 plus 273, so that is 520. So that gives you initial mass of 0.3887 kilograms. So substituting this in the previous equation, we get the temperature T2. So here initial temperature is known 520 Kelvin, and W is given, which is 121.14 kilojoule. So we get T2 to be 310 Kelvin. So now since we know the process equation, so PV raised to power n equals constant, and assuming an ideal gas equation PV equals to RT, we can express specific volume in terms of pressures and temperature, and this comes down to be P2 by P1 equals T2 by T1 raised to power n by n minus 1. So substituting the initial pressures and temperature and the final temperature which we found out, so it comes out to be the final pressure to be 0.2693 bar. So this is the final pressure. So now we have found out what is the final states. So now we can find out the heat transfer. So applying in first law for the process. So Q is M U2 minus U1 plus W. So U1 is 10,848 kilojoule per kilomole, and U2 is 6,437 kilojoule per kilomole for nitrogen for the corresponding pressures and temperature, and Q comes out to be mass into change in internal energy divided by molar mass, because it's in kilojoule per kilomole, plus the work done. So that Q comes out to be 59.93 kilojoules. So the change in entropy for this process is again same like what we did in the previous problem, is T2 P2 minus S T1 P1 is mass into the change in for a reference state, what is the change in temperature. So S naught T2 minus S naught T1 minus R ln P2 by P1. So with respect to T1 and T2, the corresponding S naught values here. So substituting the value, and R is known, we know the pressures, substituting that we get the change in entropy to be 0.1478 kilojoule per Kelvin. So in TS diagram, this is how it looks. We have two pressure isobars of 6 bar and 0.2693 bar, and we have expansion happening. So from 520 Kelvin we are coming to 300 Kelvin, 10 Kelvin, and there's a reduction in pressure, so there is expansion, and so this is what we get. So next question, we have air is compressed adiabatically in a piston cylinder assembly from 1 bar and 300 Kelvin to 10 bar and 600 Kelvin. So the air can be modeled as an ideal gas and kinetic and potential energy effects are negligible. Determine the amount of entropy produced in kilojoule per Kelvin per kg of air for the compression, and then what is the minimum theoretical work input in kilojoule per kg of air for an adiabatic compression from the given initial state to a final pressure of 10 bar. So there are two parts to the question. So first is air is compressed adiabatically. So adiabatically there is no heat transfer. So there is a adiabatic compression from 1 bar 300 Kelvin to 10 bar and 600 Kelvin. So both pressures and temperatures or both the state points are given. So straight away we can find out the amount of entropy produced or the work done and so on. So there we are assuming it to be an ideal gas and then solving. The second part of the question says what could be the minimum theoretical work to reach this 10 bar compression. So which other process can be taken? So adiabatic process follows a series of state points to reach 10 bar, and the final pressure is 10 bar and your temperature is 600 Kelvin for this case. But there can be multiple other processes which can happen. So you can have constant volume, you have constant temperature, and you have some other process. So what kind of process you can or a polytropic process, so what other process can be taken to reach this minimum theoretical work input? So how do we solve this? So if you do an entropy balance, so what we get is delta S is delta Q by T plus sigma. So delta Q by T is 0 for this case, it's internally reversible. So you have an adiabatic, reversible adiabatic, so heat transfer is 0, so this is straight away 0. So the entropy generated here in this case is the entropy change which is happening, S2 minus S1, and which is your change in temperature with and the change in pressure because of. So this is what we did in the previous problem. So with straight away we can do, and it comes out to be 0.04618 kilojoule per kg Kelvin. So this is the entropy which is generated per kg of gas. To find out the work done, so we can straight away find out using the first law. So kinetic and potential energies are 0, so delta U equals Q minus W, and since for an adiabatic process your heat transfer is also 0, so there is no heat transfer, so Q is 0, so delta U becomes equals to minus W, or W is U1 minus U2, W by M per kg is U1 minus U2. So if you see here, work is directly proportional to your change in internal energy, and internal energy is a function of temperature for an ideal gas. So U can be written as a function of temperature. So if your temperature varies, your work done will also vary. So as T2 decreases, so finally initially there is one T1, but if your T2 decreases, then your net change in heat internal energy will also reduce, and your work done will reduce. So for the minimum work done, you should have minimum temperature, and you also have to satisfy this S2 should be greater than or equal to S1, because S2 cannot be negative. For a process it always entropy is increasing for the whole process, because here compression is happening, there is some work done to the process, so it will lead to increase in entropy. So this condition has to be satisfied, and the second condition is your temperature is should be minimum. So you need to find out a state such that you have a minimum temperature and this condition still holds true. So if you plot a process Ts, so here initially you have two isobars. So the initial isobar of 1 bar and 10 bar. So this is 1 bar and this is 10 bar. So from 1 you are compressing it to state 2. So now what you are doing is you want entropy to be same as the previous case, and we have to find out what is the temperature which is minimum corresponding to this case. So we need to find out temperature T2S, which is the lowest possible temperature corresponding to the S. So that will give you the minimum theoretical work. So what we get is we know S0 T2S, so we can find out what is temperature T2 based on what is the entropy at state 2. So S0 T2S is S0 T1 plus R ln P2 by P1. So this gives you what is should be the entropy at state S2S. So that is 2.36284 kilojoule per kg Kelvin. So now with this entropy we can find out what is the temperature corresponding to pressures of 10 bar and entropy of 2.36284. So for corresponding to this case state point, your temperature comes out to be 564.1 Kelvin, and your internal energy corresponding to that point is 407.55 kilojoule per kg, and the initial U1 is 214.07 kilojoule per kg. So the minimum input is U2S minus U1. So this comes out to be 407.55 minus 214.07. So that gives you the minimum work is 193.48 kilojoule per kg. So what basically we are saying is from 1 we are going to 2, but making a system more internally reversible. So you are taking care of the friction inside, your improving the system and making it more towards an internally reversible system. Then for an adiabatic case, previously it was adiabatic but it was not reversible. So you were going from 1 to 2, so you had entropy generated. What you are trying to do is, once you are reducing this entropy generated and you are approaching reversible and adiabatic, so you get an isentropic process. So 1 to 2 is, so this will lead to the minimum work in this case. So that minimum work is 193.48 kilojoule per kg, and the actual work which happened with the irreversible process, your work is 220.71 kilojoule per kg, and this actually gives you the isentropic efficiency of the compressor. So isentropic efficiency of the compressor will be your isentropic work, that is the minimum theoretical work for a reversible adiabatic process, which is 193.48 divided by the actual work which is happening, which is 220.71. So 193.48 divided by 220.71 gives you 87.6%. So that is the efficiency of the compressor, isentropic efficiency of the compressor. So this compressor, you can say the isentropic efficiency is 87 or 88%. Our next question is, steam undergoes an adiabatic expansion in a piston cylinder assembly from 100 bar and 360 degree Celsius to 1 bar and 160 degrees Celsius. So what is work in kilojoule per kg of steam for the process? Calculate the amount of entropy produced in kilojoule per Kelvin or per kg of steam, and then what is the maximum theoretical work that could be obtained from the given initial state to the same final pressure. So both process on a property label sketch of TS diagram. So just like the previous case, instead of compression, now you have expansion which is happening. So we have the same set of equations, so just need to be careful with the signs. So the first is you have the first law which gives delta U is Q minus W, since again here it's an adiabatic expansion, so Q is 0, so you get delta U equals minus W, or W by M is U1 minus U2. So this is your first law which is giving, and then P1 equals 10 bar and T1 is 360 degrees Celsius, which is given. So corresponding to this, U1 is 2729.1 kilojoule per kg and S1 is 6.006 kilojoule per kg Kelvin. And the second one, at the second state, your pressure is 1 bar and temperature is 160 degrees Celsius. So U2 is 2597.8 kilojoule per kg and S2 is 7.66 kilojoule per kg Kelvin. So substituting this in the first expression, we get what is the work done in an actual case. So when the expander is working between a pressure of 100 bar and 360 degrees Celsius to the final pressure of 1 bar and 160 degrees Celsius. So in that case, you generate a work of 131.3 kilojoule per kg. So this is the amount of work which is actually is expected out of the expander. But this is an irreversible process. You have entropy which is generated. So how we need to find out how much entropy is generated first. So applying the entropy balance, you get delta S is your heat transfer entropy because of heat transfer and the entropy generated. So this system equals surrounding plus the entropy generated. So that's what is written. So you get the entropy generated is S2 minus S1. So we have found out what is the entropies at state 2 and 1. So substituting, we get entropy change to be is 1.6537 kilojoule per kg Kelvin. So now what we know is the maximum work, or in case of expansion, or the work which is produced in an expander, or the minimum work which is taken for a compression process, happens when your entropy generation is 0. So that is the best possible case when you are having a reversible process. So that is the best possible case, and that consumes is the most efficient possibly. So even in this case, to have a minimum theoretical work, we will have the maximum theoretical work, because it is an expansion, that is the maximum work which can be produced. So how can we understand this? So before finding out maximum theoretical work, so how do we understand this? So for example, if you take a turbine which is generating some amount of work, say 100 kilowatts. So in a reversible case, assuming it to be a super efficient turbine which follows a reversible adiabatic expansion, or an entropy is constant, so that will generate 100 kilowatts. So but in an actual case, what happens is this turbine will have inside bearings, ball bearings, and or a different kind of bearings, magnetic or whatever kind of bearings the turbine uses, and then the process, the gas itself will not be there be heat transfer and so on. So even if it's insulated, fully, then to there will be some kind of friction and other phenomena which is happening inside the turbines and compressor, which will add to irreversibilities. So part of the power which is generated will have to be used to overcome these frictions and so on. So the actual work which you get out will be lower than in case of a reversible case where what you get, because there you assume that there is no friction and so on, there is no any such phenomena which is happening which will contribute to generate entropy. So that will have an internal reversible process. So here, since it's not an internally reversible, so you have frictions and so on, so you need to spend some work to overcome this. So that's what is happening. That's why you get less power output compared to a theoretical isentropic case. And same is in case of compression. Here the whatever power is there, it is getting reduced because it's overcoming friction. In case of compression, what happens is the compression happens, so for expected inlet and outlet condition, because there is friction, you need to add extra work to overcome this friction. So that's why the minimum theoretical work is given by the isentropic case. So I hope this is clear. So with that, so now the maximum theoretical work is now given by when your entropy generated is 0. So your S2 is equals to S1. So again, for this we find out what is your entropy, constant entropy case at 1 bar. So S2S is 6.006 kilojoule per kg, which is same as S1 for a final pressure of 1 bar. So this lies in a two-phase case. So at 1 bar we can compare what is your entropy. So it will lie between your vapor and liquid entropy. So the quality at exit comes out to be 0.7765. So again, this is a problem in case of a turbine which you don't require to have this amount of liquid in the turbine. So what will happen is, because liquid and there are different in densities, it will create additional problems. It will have vibration, it will have erosion and so on, other problems. So practically this is to be avoided, but we are making some theoretical calculation. So how does it matter? So we get quality here. So quality comes out to be 0.7765. So corresponding the internal energy also comes out to be, we can find out using the quality, it comes out to be 2039.3 kilojoule per kg. So that is your internal energy. So with this we can now find out, because it's still a reversible adiabatic process. Previously it was an adiabatic, but now we are making sure that it follows a reversibly adiabatic process for generating a maximum theoretical work. So you get U1 minus U2S. So that is U1 is 2729.1 minus U2S is 2039.3. So your work generated per kg of steam comes out to be 689.8 kilojoule per kg. So previously in actual case what was produced was 131.3 kilojoule per kg, but following a reversible adiabatic case, making sure that entropy generated is 0, the work then has increased from 131 to 689.8 kilojoule per kg. So I said the practical problem is you cannot have this quality. So that is a practical aspect. And then okay, so this is the theoretical efficiency, maximum efficiency, and maximum work, and this is the actual work. So how the efficiency of turbine can be found out. So what is the efficiency of turbine? What is the actual work divided by the maximum, that is 131.3 divided by 689.8, that gives you an efficiency of 19%, 19. That is the efficiency of this turbine or the expander, piston cylinder arrangement assembly. So this is an expander. So the efficiency is 19%. So isentropic efficiency is for an expander, it is actual by the maximum which is the isentropic work. In a compressor it will be reverse of it, so it will be isentropic by the actual, because in compressor actual will always be greater than isentropic work, because isentropic is the minimum work. In case of expander, the isentropic is the maximum work, so it will be at the bottom. So that is on expander. So next is, consider the solid rod at a steady state. The rod is insulated on its lateral surfaces, but energy transfer occurs at the rate q1 into the rod at location 1, and energy transfer occurs at the rate q2 out of the rod at location 2. So applying the energy and entropy rate balances to the rod as a system, determine which temperature T1 or T2 is greater. So what is the condition to say how the heat transfer is? So this is, can say in broad sense, explains you the second law, a simple problem to explain the second law. So because the first law says energy conversion and so on, but it never says the direction of conversion, the direction of heat flow and so on. So that's why the second law starts with two statements, which addresses the directionality of the process. So this is a classic example on those. So we have a solid rod which is at steady state. So in steady state, there is, with respect to time, there is no change. So what is given is, you have consider a rod, the surface is insulated except the two ends, and from one end you have heat which is coming in, say q1, and this surface is at temperature T1, and the other end you are losing heat q2, and this is at surface T2. So there is heat which is coming in and which is heat is going out. So this is the process which is happening. So we need to apply energy and entropy balances on the system and say which is the temperature T1 and T2. So normally with our physical experiences around, we know that heat always flows from a higher temperature to a lower temperature. That's what we have to prove here. So we have to prove it using the equations. So what we'll do is, we'll apply the energy balance first. So du by dt equals q, your q net minus w net. So there is no work transfer, so w is 0. Since it's a steady state and there is no variation in temperature, so u is also 0. So what this is applying control volume. What is happening is, there is some q which is coming in and there is q which is going out. So this says that whatever heat which is, because it is in steady state, whatever heat is coming in will go out, and there will be no change in internal energy of the system. So that's what steady state says. So you have q which is coming in and that is going out, so same quantity, q1 equals q2. So that is the first equation which we get, and the second is what we applying an entropy balance. So what we get is ds by dt equals your integral del q by t plus sigma is the entropy generated. So the change in entropy of the system with respect to time is 0. So this is 0 equals, so the integral del q by t. So there is q1 which is coming in and q2 which is going out. So we have q1 by t1 minus q2 by t2 plus your sigma, which is the entropy generated. So rearranging this, what we get is, q1 is because q1 is q2, so q1 bracket 1 by t1 minus 1 by t2 plus sigma, this should be equal to 0. So we taking a difference in rewriting the expression, we get t2 minus t1 to be minus t1 t2 by q multiplied by sigma. What we know is, your entropy cannot be negative, So sigma is always positive, and since the heat transfer is happening, Q is also positive. So we know that temperature cannot be negative in absolute Kelvin. So T1 and T2 is also positive. So the right hand side of the expression, so T1 T2 by Q multiplied by sigma, will always be positive. So this says that T2 minus T1 is negative. So T2 minus T1 can only be negative when your T1 is greater than T2. So T1 should be greater than T2 for the process to happen. So, and that's what we know, because Q is flowing from T1 to T2. It can happen only at from highest temperature source to a lower temperature source, and that's what we have proved here. So T1 should be greater than T2. So, and this is equivalent to the Clausius statement of second law, stating that without work interaction, heat cannot flow from a lower temperature to higher temperature. It can only flow from hot to cold. The next question is, we have a closed rigid tank which contains 5 kg of air initially at 300 Kelvin and 1 bar. The tank is in contact with the thermal reservoir at 600 Kelvin, and the heat transfer occurs at the boundary where the temperature is 600 Kelvin. A stirring rod transfers 600 kilojoule of energy to the air. The final temperature is 600 Kelvin. So the air can be modeled as an ideal gas with CV of 0.733 kilojoule per kg Kelvin, and kinetic and potential energy effects are negligible. So determine the amount of entropy transferred into the air and the amount of entropy produced, each in kilojoule per Kelvin. So we are two kinds of transfer, both heat and work transfer are happening here. So you have a closed container and the mass is given air, and the initial condition of 1 bar and 300 Kelvin is given. So now this content is being, air is getting heated from a temperature source of 600 Kelvin, and the air is reaching the final state of 600 Kelvin. Since it's a closed system, we don't know the pressure, so we need to find out the pressure, but we know it reaches a temperature of 600 Kelvin, and since it's a closed system, your volume is constant. And during this heating, there is also a work transfer which is happening by stirring the air. So by stirring, and so it's making sure that your content inside is at same temperature. So the stirrer which has been added, and the stirrer takes work of 600 kilojoules, and Cp is given, and we need to find out what is the amount of entropy transferred into there and the amount of entropy produced, or in sense entropy change of the system and the entropy generated. So the first is, since the volume is constant, we can say V2 is specific volume V2 is equals to V1, because the total volume divided by mass, because mass is constant. So we can take specific volume V2 equals specific volume V1. So what we get is P2 equals T2 by T1 by multiplied by P1. So P2 is 2 bar, because the temperature ratio is 2, so pressure is also will be 2. So P2 is 2 bar. So applying the first law, we get delta U is Q minus W. So we get Q equals M U2 minus U1 plus W. So now since we know the temperatures, initial and final temperature, and we know the work done, we can find out how much heat has been transferred to the air. So Q is mCV delta T. So mCV T2 minus T1 plus W. So we know mass is 5 kg and the Cv of air is 0.733, which is given in the problem. So 0.733 into 600 minus 300 plus your work transfer, which is 600 kilojoule. This is negative because work is transferred to the system. So we get minus 600. So this total quantity comes out to be 499.5 kilojoule, which is the amount of heat which is being transferred to the air. And this is positive, so it says that heat is transferred to the system. Now the heat is being transferred at the boundary. So the amount of entropy transferred with the heat transfer is Q by T, because it is constant temperature. So we get the entropy change is, entropy transfer is 0.8325 kilojoule per Kelvin. So that is the amount of entropy which has been transferred, and the number entropy produced is S2 minus S1 minus Q by T plus sigma. So integral Q by T, because T is constant, we can take Q by T. So we have to find out sigma, what is the entropy generated. So for that it is M S2 minus S1 minus Q by T. So S2 minus S1 we can find out straight away. Instead of TdS is dH minus VdP, we will take TdS is du plus P dV. So dV is constant 0, so dV is 0, so we get only Cv delta T. So we get ds is Cv by T dt, so we get Cv ln T2 by T1. So S2 minus S1 is Cv ln T2 by T1. So substituting your temperature, we get entropy change in the system is 0.5081 kilojoule per kg Kelvin, and we have found out how much is the entropy transfer, which is 0.8325. So the entropy generated comes out to be 1.7079 kilojoule per kg Kelvin. So the net entropy increase in the system is S2 minus S1, which is your 1.7079 plus 0.8325, or 5 times of 0.5081. Mass is 5, so 5 into 0.5081 both gives you 2. Your entropy increase to be 2.5404. So next question, we have a heat pump cycle which operates at steady state and provides energy by heat transfer at a rate of 15 kilowatts to maintain a dwelling at 22 degrees Celsius, and the outside temperature is minus 22 degrees Celsius. The manufacturer claims that the power input required for this operating condition is 3.2 kilowatts. Applying energy and entropy rate balance, evaluate this claim. So what we have is a heat pump cycle. So we know what is heat pump. So which transfer heat from a low temperature to a higher temperature, and the higher temperature is your desired heat transfer, and it takes work. So instead of cooling, we are focused on the heating part. A refrigerator focus on the cooling part. Here you are concerned about the heating part. So your low temperature is your ambient, and higher temperature is your room or whatever space has to be heated. So that's what is happening here. So you are outside, which is at minus 22 degrees Celsius. So corresponding Kelvin is 251 Kelvin. And here from here you are taking away some here Q, and to do that we are supplying some work and pumping the total heat back to the room, and this is at 22 degrees Celsius. So for this we need to find out, apply energy balance and entropy balance and find out whether this claim is true. So applying the first law, we get QC to be QH minus W, because Q net is W net for a cycle. So C is QH minus W. So QC is 11.8 kilowatts. So that is the amount of heat which is extracted from the ambient, and 15 kilowatt is what is dumped in the room. So applying the second law or the entropy balance, so since there is no system inside, so H2 minus H1 is 0. So what we get is QH by TH minus QC by TC plus the entropy generated in the cycle. So the entropy generated in the cycle comes out to be QC by TC minus QH by TH. So substituting, we get W sigma cycle to be 0.004 kilowatts. So this says that this is positive. So this cycle satisfies the second law of thermodynamics, because sigma cycle should always be greater than or equal to 0. So this is positive, so this is greater than 0, and so the cycle is possible. So the second is the maximum possible coefficient of performance for a pump cycle operating between TC and TH is, so the maximum COP is TH by TH minus TC. So that comes out to be, so this is the second way out to be. So one says first we found out what is the entropy generated during the process. So if this is greater than 0, so that a cycle is possible. The second way is we know the maximum efficiency provided by a heat pump or any cycle is lower than the Carnot efficiency or the reversible cycle efficiency. So the reversible cycle efficiency or the Carnot heat pump is TH by TH minus TC, and that COP comes out to be 6.682. Your hot source temperature is 294 divided by your hot source is 294 minus 251, which is the ambient temperature. So that gives you 6.682. But in the actual COP for this heat pump is, we know the heat which is supplied to the room, which is 15 kilowatts, and how much work is been used by the heat pump, and that is 3.2. So 15 by 3.2 gives you the actual COP, or the claimed cycle performance is 4.6875. Since this coefficient of performance is lower than the maximum theoretical, which is the Carnot COP, since this is lower, so the cycle is possible, and this it will not violate the second law of thermodynamics. So this is another way of solving it. So next question, air enters a turbine operating at steady state at 8 bar and 1400 Kelvin and expands to 0.8 bar. The turbine is well insulated and kinetic and potential energy effects can be neglected. So assuming ideal gas behavior for the air, what is the maximum theoretical work that could be developed by the turbine in kilojoule per kg of air flowing? So we have turbine. So previously this is just like the previous problem. So we need to find out what is the maximum theoretical work. So what we know is initially it is at 8 bar and 1400 Kelvin, and we need to expand into 0.8 bar. So what basically is asking is the process is assuming a reversible isentropic process. What is the work generated? So to find the work, the mass balance, the mass will remain constant, and then applying energy balance. So dou E C by dt. So it's a flow equation because the open system turbine. So applying steady flow energy equation, we get Q minus W plus M H1 minus H2 plus V1 square minus V2 square by 2 plus G Z1 minus Z2 equals 0. Since we are neglecting kinetic and potential energy change, so V1 square terms and Gz terms, potential energy terms will go away, and since the turbine is insulated, the Q will also vanish, so Q is 0, and since steady state, dEC by dt is also 0. So what we get is Wc by Wcv divided by M is H1 minus H2. So the maximum work is generated when you are the minimum entropy, and that can be showed from the entropy rate balance. So we get ds by dt integral summation of q by t plus m s1 minus s2 plus sigma. So this is the entropy balance. So q by t is 0 because there is no heat transfer adiabatic process, and since steady state, so ds by dt is also 0. So what we get is m s1 minus s2 plus sigma cv equals 0. So we get entropy generated by m is s2 minus s1, and we get maximum work only when your entropies change is 0. So s2 minus s1 to be 0 or s2 equals s1. So the process happens when s2 is greater than s1, but the maximum is generated when s2 is equals to s1. So that's what we want. So writing that, what we get is s2 minus s1 is 0. So what we get is s0 t2s minus s0 t1 minus r ln p2 by p1. So we get we can find out t2s. So t2s s2 s0 t2s is 2.70119 kilojoule per kg Kelvin. So interpolating for air from the air table, we get t2s to be 788 Kelvin. In the corresponding enthalpy corresponding to T2s and 0.8 bar comes out to be 808.8 kilojoule per kg. So finally applying it in the first law, so which we got W by M is H1 minus H2 S. So substituting the values, H1 is 1515.42 minus H2S is 808.8, we get the work to be 706.6 kilojoule per kg of air. So that is the amount of work, maximum work, which can be generated in the turbine. I think this is the final problem for today which I have prepared. So the question states, an inventor claims to have developed a device requiring no work or heat transfer input, yet able to produce a hot and cold air stream at steady state. So data claimed by the inventor are shown on the control volume in figure. So the ideal gas model can be used for the air, and kinetic and potential energy can be neglected. So evaluate this claim. So inventor is claiming that he has found a device which takes some air which is at 20 degree and 30 degree, and you get out there is no heat transfer, there is no work transfer, but you are able to heat and cool the same stream. So what is claiming is you are getting air at 20 degree Celsius and 3 bar, and out you are getting air at 60 degree Celsius and 2.7 bar, and also at 20 degree 0 degree Celsius and 2.7 bar. So one part of air is getting heated up and one part of the air is getting cooled. So since the air is getting splitted, so because of mass balance, so m1 should equal to m2 plus m3, and we need to evaluate whether this kind of process is possible and whether will it violate second law. So that's what we have to evaluate, whether this is possible. To that, first, as I said, we will do a mass balance. This is what we get, m dot 1 equals m dot 2 plus m dot 3, and since we are neglecting kinetic and potential energy, and also there is no heat transfer and work transfer, so what we will get is the energy which is coming in, which is m dot 1 plus h1, sorry, minus m dot 2 h2 minus m dot 3 h3. There is a negative sign here, I think it's a mistake here. So y is a fraction, we are converting this into fractions now, because we have two mass unknowns, we are can convert into fraction, we can be simplified. So y is m2 by m1, so we can combine the mass and energy balance. So we get y is h1 minus h3 divided by h2 minus h3. So we can find out what is the enthalpy. So for air, we can estimate the enthalpies corresponding to this pressure and temperature. So for 20 degrees Celsius and 3 bar, and similarly at 60 degrees Celsius and 2.7 bar, and 0 degrees Celsius and 2.7 bar. So what we get is h1 minus h3 is 293.2 minus 273.1 divided by 333.3 minus 273.1. So this comes out to y is 0.334. So for stream 2 which is getting heated up, so 33% of the air which is coming in is getting heated up to 60 degrees Celsius, and the rest 66.6% is getting cooled to 0 degrees Celsius. So this is the mass ratios. So next we need to evaluate whether this process is true. So we have used the mass balance and energy balance to find out what is the ratios in the mass to be having, but we still don't know whether the process is possible. So for that we need to we'll apply the second law and see if the entropy generated is greater than 0. If that is greater than 0, then this process is possible, and without heat and work transfer, you can simultaneously heat up and cool down the stream. So the entropy rate balance applying for the steady flow equation, we get dou S by dou T is 0. So plus summation of Q by T, which is also 0 because there is no heat transfer, plus the entropy of stream coming in and going out. So plus m dot 1 S1 minus m dot 2 S2 minus m dot 3 S3 plus sigma SV. So sigma by m1 comes out to be So sigma by m comes out to be S3 minus S1 plus y S2 minus S3. So substituting the entropy values, we get S dot T3 is minus S naught T1 minus R ln P3 by P1. So we get delta S3 minus S1 is minus 0.040763, and similarly S2 minus S3 is 0.1996 kilojoule per kg Kelvin. So substituting the total, we get finally the entropy generated to be 0.0295 kilojoule per kg Kelvin. So this says that sigma value is greater than 0. So this process is possible, and actually we do have a device which provides a similar kind of process. It's called as an vortex tube. So where you supply high pressure air, so because and the air flows through an orifice and through and flows as a vortex. So the innermost stream will have one velocity, and the outermost stream will get heated up because there is a centrifugal force and so on. What you will get is a hot stream and a cold stream. So this is similar to that. We are passing at high pressure stream, and because of the expansion, so one stream is heating up, and similarly the other stream is getting cooled. And this is possible, and this device is called an vortex tube. And here that we have proved that in the vortex tube there is an entropy generated, and this device is possible, and it will not violate a second law of thermodynamics. So with that we'll end the session for today. So I prepared what I have finished what I prepared for today. So next week we'll look at some more problems regarding entropy, applying entropy to processes, and see how to solve those. So that will for next week, and after solving that we can then proceed to see some cycles. So with that, that's it for today. Thank you. Close the session. Thank you.